Okay. Next from equation 36, right. So, equation 36 it was pki, that was pik, and this is your pki, right. So, this is the expression for this thing. So, here also find out p21 also, right, like k is equal to 2, I is equal to 1, in this expression you substitute. If you do so, that will be the expression for p21, that is equation 36, right. So, that means at all the parameters you put it here, then you will get p21 is equal to your minus 1.744 per unit megawatt, that is minus 174.4 megawatt, right. If you see P12 here 181.89 megawatt, right, and that means power, it is positive, means power is flowing 1 to 2, right, and here at the P21 it is minus 174.4 megawatt, then power actually flowing from your what you call 1 to 2, but as P21 is showing minus, right, that means in between, and this one is your P12, this one is 181.89, it indicate difference, indicate that resistive loss in the line, right, that we will see after this. So, similarly your this is P21, similarly P31 using the same equation 36, right, k is equal to 3, I is equal to 1, if you put all the parameters, P31 will also become minus 1.95 per unit megawatt, that is minus 195 megawatt, right. So, that means actual direction of the power flowing is 1 to 3, because it is minus sign is coming, right. So, next is your P32, same way you can compute, right, the same equation you can use and put your k3 I, k is equal to 3, I is equal to 2, expand this and your what you call put this, and there you put all the values, you will get P32 is equal to 49.6 megawatt. All these results are after second iteration only, right. Now, real power losses in line 1, 2, 1, 3 and 2, 3. So, P loss 1, 2 actually is equal to that we have shown before, no, that P line flows P12 plus P21, that is 181.89 minus 174.4, that is 7.49 megawatt. Similarly, P loss 13, that is P13 plus P31 200 minus 195, that is 5 megawatt, and P loss 23, that is P23 plus P32, that is minus 49.03 plus 49.6, that is 0.57 megawatt, right. So, these are the result for the losses after your what you call that your second iteration, that is a real power loss, right. Similarly, your reactive line flows we calculated from equation 35 and 37. So, again like your QIK expression is given in equation 35, right. So, there you just put I is equal to 1, k is equal to 2 and this expression, and put all these parameters, you will get Q12 actually is equal to 0.894 per unit megawatt, that is multiplied by 100 MB is the base. So, 89.48 megawatt, right. Similarly, Q13 also you compute, put all the values. So, Q13 will become 108.8 megawatt, right. So, similarly, Q23 also you compute, right. So, all these directly I am not writing the formula for Q23 again, just you can do it of your own, right. So, all these things are details have been explained, right. So, you can do it. So, Q23 will become minus 47.46 megawatt, right. Now, similarly from equation 37, that is your QKI, that was QIK and that is QKI. This expression is given 37, but note that charging admittance is not considered. So, it will be 0, this term will be 0, right, and QKI also for QIK also charging admittance was 0, because we have not considered that, right. So, if you calculate Q21, then it is coming minus 74.6 megawatt using equation 37. Similarly, Q31 you compute upon substitution of all, you will get it is minus 94.69 megawatt, right. So, then you calculate Q32. that is your Q32. Again the same expression, put all the values, not writing those expression again and again, right, understandable now. Right. So, this is coming Q32 is equal to 48.66 megavar. Now, reactive power losses in line 1 2, 1 3 and 2 3, same as before. So, Q loss 1 to Q12 plus Q21. So, you will get 14.88 megavar. So, Q loss 1 3 is equal to Q13 plus Q31, you will get 14.11 megavar, and Q loss 2 3 is equal to Q23 plus Q32, that is coming 1.20 megavar. Note that all the results given above are computed after second iteration only. It is not converged result. For that convergence, you have to make a more number of iterations and you have to test the convergence, that whatever convergence procedure I have said, right. Next is that this is the example we consider for when all buses are your PQ type buses, right. Now, next we will take an example that will consider PV bus also, and you can see that how we can accommodate PV bus in the Gauss-Seidel method. After Gauss-Seidel method, we will come to the Newton-Raphson method, right, and your coupled, decoupled and fast decoupled, right, load flows, and then we will see that your transformer, your tap changing transformer representation, the pi model, and after that I will tell you the P and PQV your bus accommodation in that load flow studies, that how one can do this and what is the your significance of it, right. So, next example is that your same data we have taken, except one thing, that this is actually in this case this is a slag bus, bus 3 is a PQ bus, that same load data as before 138.6 megawatt and reactive load is 45.2 megavar, right. And this bus is a PV bus, So, here for bus 2 voltage magnitude is specified. At PV bus, P has to be specified and voltage magnitude has to be specified. So, voltage magnitude V2 is equal to 1.0 per unit, it is specified, and load that is 305.6 megawatt, Pg2 is also 50 megawatt, but no other thing has been mentioned, right. That means PV bus means you have to find out that your what you call Q is not given, right. So, so that means in PQ bus V and delta are unknown for this bus, V3 and delta 3 you have to find out, and for this bus as your Q and delta 2 has to be obtained, because voltage magnitude specified, real power also specified, right. So, in this case we will show only your what you call that couple of iterations, right. I have to check whether I have made it 2 iterations or 3 iterations, right, but how to make it, but no Q limit, nothing will be considered here, just to show you that how things can happen, right. So, same as before, PL2 is given 305.6 megawatt, Pg2 is 50 megawatt, right. Therefore, P2 is equal to Pj2 minus PL2, that is minus 255.6 megawatt. Therefore, P2 is equal to minus 2.556 per unit megawatt, same as before, right. And similarly, so this is again 3 bus problem. So, similarly, P3 is equal to Pg3 minus PL3. So, there is no generator at bus 3. So, it is 0 minus 138.6 megawatt, that is minus 138.6 megawatt. So, it is divided by 100. I am not dividing it 100, but if you divide by 100, that is 100 MVA is the base. So, minus 1.386 per unit megawatt, right. Similarly, for Q3 is also Qg3 minus QL3, that is minus 45.2 megawatt. So, divided by 100, it will be minus 0.452 per unit megawatt. Now, slack bus voltage is same 1.05 plus j 0.0, right. Now, PV bus magnitude of voltage magnitude V2 is equal to 1, right. That means, V2 0, actually we can take 1 plus j 0. In this case, what we will do that the way we solve that your I will follow this thing different slightly different procedure of this iterative method, right. So, what we will do that V2 0, although this voltage magnitude actually constant, right. So, you assume V2 0 is equal to 1 plus j 0, that means magnitude is 1, but initial angle is 0, right. So, this way we assume, but magnitude will always remain constant, magnitude will be untouchable, right. It is given, and for PQ bus V3 0 1 plus j 0, right. So, but this PQ bus V3 both magnitude and angle will vary, but here magnitude has to be kept fixed, right. So, this one your bus 2 is a regulated bus, that is PV bus, right, where voltage magnitude and real power are specified, right. And for the PV bus first the reactive power is computed using equation 16. Just let me find out where is equation 16, right, I will tell you. So, here it is, right. So, this was your equation 16 and n is equal to 3, this is equation 16, then n is equal to 3, because at bus 2 it is your PV bus. So, in that bus your what you call Q2 is not known, right, Q2 is not known. So, we have to see that how iteratively we can make it, right. So, what you will do it, that from this equation n is equal to 3 you expand for I is equal to 2, right, because bus 2 actually is a PV bus, right. So, put I is equal to 2 and k is equal to 1 to n, because n is equal to 3, because you have a 3 bus problem you are solving, right. Therefore, if you put I is equal to 2 and minus, it is minus sign, a minus sign is there, right. So, it is k is equal to 1 to 3, then it will magnitude V 2 V k magnitude y 2 k sin theta 2 k minus delta 2 plus delta k. For k is equal to 1 to 3 you expand this equation, right. If you expand this equation, right, then you will get this q 2 is equal to this one, that minus magnitude V 2 magnitude V 1 magnitude y 2 1 sin theta 2 1 minus delta 2 plus delta 1, then minus magnitude theta 2 square magnitude y 2 2 sin theta 2 2, right, minus magnitude V 2 magnitude V 3 magnitude y 2 3, right, sin theta 2 3 minus delta 2 plus delta 3. Now, if you want for iterative procedure, right, iterative procedure, right, then q 2 p plus 1, right, then V 2 p, right, V 1 is a slack bus. So, no question of putting this one, y 2 1 is a constant, sin theta 2 1 minus delta 2 p, because bus 2 is a PQ bus, delta 2 will also vary, that is why it is p, plus delta 1 is the slack bus angle, it is a 0 actually, right. Then minus V 2 p whole square, right, because it is V 2 square, right, and this one, this magnitude 1, this V 2 p square magnitude 1, actually no need to put p, because this is actually bus 2 is a PV bus, this voltage magnitude will remain constant. So, minus V 2 square rather, right, no p, then magnitude y 2 2 sin theta 2 2 minus, again here also magnitude of V 2 will remain constant, no need to put p, right. So, magnitude V 2, because your bus 2 is a PV bus, so V 2 is fixed, magnitude V 2 is constant, so no need to put p, right. Then into V 3 p capital Y 2 3 sin theta 2 3 minus delta 2 p plus delta 3 p, but bus 2 that delta 2 p you have to put it here and here, because it is a PV bus. So, delta is varying, but magnitude V 2 always constant. So, no need to put p, right. So, this is your q 2 p plus. Now, y matrix is the same as example 1, same y matrix, right. So, no change. So, in that case, so these are the y matrix, this magnitude and angle, magnitude and angle, magnitude and angle, all y 2 1, y 2 2, y 2 3, right. So, now iteration set p is equal to 0. Look, we are not computing at present any voltage or anything, only we are computing q power injection at bus 2, right. Therefore, because after that we will see how we will go for iterative process, right. So, in this case that q 2 1, you when p is equal to 0, when p is equal to 0, here you write q 2 1. So, this is be this q 2 0, this equation will be, right, that your magnitude your this one what you call here also magnitude V 2 p, this p also should not be there, because magnitude voltage is this thing is your magnitude is constant. So, here also this is not required, here also this is not required, here also this is not required actually, right, this is not required. So, and rest your the way they are your given delta 2 0, delta 2 0, delta 3 0 all are there, delta 1 anyway it is 0 angle, right, because it is slack bus, and slack bus voltage also no question of iteration, because it is fixed, right. So, with that you put q 2 1. So, V 1 is 1.05, angle delta 1 0.0, magnitude V 2 0, actually it cannot be 0, because it is magnitude will always remains constant, right. and delta 2 0 is equal to 0.0 degree and V3 0 is equal to 1.0 and delta 3 0 0.0. All this you substitute here, you substitute here, you substitute here, right. If you do so, then what you will get? You will get Q21 values, put and simplify, right. You can compute Q21 is minus 1.0067 per unit megabar. This is the value of Q21, right. Now, the value of Q21 is taken as a net reactive power injected at bus 2, right. That is Q2 is equal to Q21 is equal to minus 1.0067 will take, right. So, first what we are doing for PV bus? We are trying to first after we are trying to compute that at PV bus the reactive power injection, right. So, therefore, we will take that Q2 is equal to this much as reactive power injection at bus 2. Iteratively you have to obtain iteratively, right. So, Q2 is equal to Q21, that is a Q2 value in the very first iteration, right. I hope you are understanding this, right. Once it is done, then instead of writing equation V2, I am writing VC2 P plus 1, because this is not the correct value of the your what you call bus 2, because bus 2 is a PV bus and its voltage magnitude is 1, but using this equation it will never be magnitude will never be 1, right. So, but same equation we are writing 1 upon Y22 P2 minus J, instead of Q2 we are writing Q2 P plus 1, because that Q2 P plus 1 that equation your what you call that this you have to obtain iteratively. So, this Q2 P plus 1, this is Q2 P plus 1, right. So, we are putting minus J Q2 P plus 1 upon V2 P conjugate minus same as before Y21 V1 minus Y23 V3 P, right. That means, this is Vc2, not just making Vc2. So, when P is equal to 0, when P is equal to 0, then Vc21 is equal to 1 upon Y22 P2 minus J Q21, Q21 is already computed here, Q21 is already computed here, right. Here it is and P2 already earlier we have made it the net injected power at bus 2, those data known, right, minus Y21 V1 minus Y23 V3 0, this is the thing. Now, same as before, you compute P2 minus J Q21, multiply this whole thing by 1 upon Y22. So, you have to compute P2 minus J Q21 upon Y22 minus Y21 upon Y22 minus Y23 upon Y22, right. So, if you do so, then P2 was minus 2.556 and Q2 was just Q21 was just minus 1.0067 we have computed. So, substitute all divided by Y22, you will get 0.04725 angle 2 to 1.9 degree. And next capital Y21 upon capital Y22, earlier we have got it, that is minus 0.3846. Similarly, capital Y23 upon capital Y22, earlier you have got it minus 0.6153. With this equation Vc21, that means this equation, that is this equation will become your 0.0472 angle 221.9 degree divided by V20 conjugate plus 0.3846 V1 plus 0.6153 V30, right. So, with this all V20 known, V1 known, V30 known, everything is known, then you substitute all and then you simplify, you calculate, compute. It is coming Vc21 0.98396 minus J 0.03155. If you take its magnitude, it is never 1, right, but we have to make it 1. So, what we will do for PV bus consideration in Gauss Seidel method? What we will do, since V2 is held constant at 1.0 per unit, right, only the imaginary part of Vc21 is retained. That means, what we will do, that imaginary part whatever we have got it using that Q2 you are considering that Q2 injection, that imaginary part will retain, but this one will compute, this one will find out. How we will do this? Now, that means, imaginary part will take F21 is equal to, because your V2 actually V2 is equal to your say E2 plus JF2, right. This way you are taking. That means, your magnitude of V2 is equal to root over E2 square plus F2 square. That means, otherwise you can write E2 square plus F2 square is equal to magnitude of V2 square, right. That means, E2 is equal to your magnitude V2 square minus your F2 square to the power half. right, whatever value comes. So, what same thing we are doing it here, that your F2 is here we got minus 0.03155. So, this is my F2, right, this is my F2. So, and its real part is obtained from this equation E21, just now I wrote, no, V2 square minus F2 square to the power half, same thing, that your V2 square root over V2 square minus F2 square, here actually in bracket one, although it will be positive, one minus sign is there before, here it is minus, because here it is minus. So, one minus is there, right. So, that means your this one, but V2 will be held constant at 1. So, this one we have kept fixed, right, minus your here also minus is missed. So, this is also your minus, right. So, that means it will become E21, that is 0.9995. Then we will take V21 actually 0.9995 minus this one, this will give you magnitude 1, because based on that only we got this E, right, and its angle is be minus 1.807 degree. That means this one using Q2 injection, that is we got 0.98396 and minus j 0.0315, but corrected value you correct it, right, by considering this approach, such that your this one magnitude if you take, it will become 1 now, and angle will be minus 1.807 degree. That means, this V2 in first iteration magnitude is fixed because PV bus, but angle we have got it, right. So, similarly your but bus 3 is a PQ bus, So, in that case the same equation, same way you can write this equation V3 P plus 1 upon y 1 upon y33, capital Y33, P3 minus JQ3 upon V3 conjugate minus capital Y31 V1 minus capital Y32 V2 P plus 1, because V2 already computed. So, we are writing V2 P plus 1, not V2 P, right. So, with this with P is equal to 0, the first iteration V31, all these things are there, this is the equation, right. So, P3 minus JQ3 upon V30 already we have computed before, it is same here, right, and this one also same, this one also same, right. So, with that you put all these values for in the equation of V3, all these values. So, you will get V31 is equal to 1.0101 angle minus 2.03 degree. V3 is a PQ bus. So, no question of this thing, directly you are getting. So, after first iteration you got V21 is equal to magnitude remain constant because PV bus, right, angle minus 1.807 degree, and V31 is 1.0101 angle minus 2.03 degree, right. This is after first iteration. Now, at least what you have to do is, now again you have to compute Q2 for the second iteration, you have to find out again, and you have to go for the correction to the real part of that PV bus voltage magnitude, right, real part of the PV bus voltage. So, similarly set P is equal to 1, then this Q22 will be the same equation will come, right, and all the values. Now, delta 1 is 0, delta 21 is computed this much minus 1.807 degree, delta 31 minus 2.03 degree, magnitude V1 is 1.05, magnitude V2 always constant 1, and magnitude V3 in first iteration 1.0101 per unit, right. So, all these values you substitute here, right. If you do so, then you will get after calculation Q22 will be minus 1.0507 per unit, right. This Q2 will get, and once you get this, in same way you calculate your what you call that VC2 computation, right. So, you will get that VC2 in the second iterations will be in this form, same thing again you make it, this is constant, and you will find with that values of Q, this is more or less same, right, this 0.04725 almost same, right. So, when you and all the initial value, all the values are known to you, so you substitute all the values, right. So, in that case what we will get VC22 in the second iteration 0.9888 minus j 0.05244. This one we can write E2 2 in the second iteration real part plus j imaginary part F2 2 in the second iteration. Now, F2 2 we are retaining, this is we are taking minus 0.05244, but E2 2 because voltage magnitude at bus 2 has to be held constant. So, it is 1. So, E2 2 is root over 1.0 square minus this minus 0.05244 whole square, that is coming 0.9986 right. That means V22 actually 0.9986 minus this one, although with a reactive power injection it was coming like this, but it is corrected right, and it is now 0.9986 and minus j 0.05244. So, V22 actually one angle minus 3 degree, magnitude is fixed again, but only angle is varying right. Similar way that V32 you can compute, again you compute all these values, this will remain constant, these are also constant because already computed, only these values you have to substitute right. Therefore, V32 you will get in V23 means the second iteration right, you put it, you will get it, it is 1.0093 minus j 0.04619. So, V32 is 1.0103 angle minus 2.6 degree. So, after second iteration that V2 and V3 in the second iteration, it is one V2 magnitude fixed, one angle 0 minus 3 degree, and this one 1.0103 angle minus 2.6. This is the result after second iteration. Actually, I have done it up to second iteration right. So, this is your what you call that Gauss-Seidel method, that how one can use a Gauss-Seidel method solving load flow studies right. So, only thing is that in Gauss-Seidel method that it takes more number of iterations, because convergence characteristic actually is a linear right. If time permits at the end, then I can show you the proof that convergence characteristic of Gauss-Seidel linear and Newton-Raphson it is a quadratic. If time permits, then not at the end of this topic, but at the end right. If I find 1 hour extra time, then I can show you the proof right. So, question is that in whatever two examples we have seen, it is a 3 bus problem only right, and with that also you have seen the huge computations required right. I am giving you lecture, so making all these things, but when you will calculate it, it will take more time right. So, this is one thing, and you have to make all the calculations correctly, and all these angles 175, 183 or 229, all these angles when you are making it, check carefully which coordinate you are, accordingly you take the angle. Sometimes calculator you will take something, calculator may give different angle maybe this way. So, you have to see that which coordinate this thing are, and accordingly you take the angle, accordingly I have taken right, otherwise you may there is a possibility of mistake right. So, be careful about that, and all the calculations Y matrix other thing and charging admittance are not considered right, but your what you call this, but you have got the your what you call got some ideas that how to solve load flows using in Gauss-Seidel method for considering when buses are PQ bus or buses and bus, another thing is the PV bus right. So, but these are the thing, but different versions of consideration of PV buses are there in the literature for Gauss-Seidel method, but I have given you this version because I found this version is quite easier right. Next we will take Newton-Raphson method, but before that little break. Thank you.